Hello, today I'll be recording the F equals to MA problems 13 and 14 for the year 2025. So, the following information applies to problems 13 and 14. Angela the puppy loves chasing tennis balls, so her owners built a tennis ball launcher. It fires balls along the floor at some initial speed, applying no rotation to them. The balls initially slip along the floor and then start rolling without slipping. Ignore the potential deformation of the ball and floor during this process, as well as air resistance. Which of the following plot pairs could show the linear speed v and rotational speed omega of one of the balls over time? Assume the floor has a constant roughness. I'm not showing the actual plot pairs, and we'll just see if we can derive them on our own and see if it matches with the solution for yourself after this video. Let's see how it works. Okay, so this is what I did for problem 13. So notice here that I have a free body diagram of the sphere of one of the tennis balls rolling on the ground. You see your normal forces. You have the frictional force as the ball attempts to roll along the floor. Okay, sorry about that. The normal reaction and its weight that's pulling it down. And then here I also have some of the velocities. Omega t would be the rotational velocity at time t, and vt is the velocity at time t. Let's first find the linear velocity. Well, in this case, at equals to sigma of ft divided by m, where m is the mass of a tennis ball, implying that at equals to negative mu g, because remember, n is equal to mg from the vertical standpoint. So we can just plug n equals to mg, and then at equals to minus mu mg divided by m, which is equal to negative mu g. Therefore, if we use the velocity equation, we get velocity at time point t equals to the original velocity plus alpha t times t. Well, alpha in this case would be constant. So we end up getting that velocity at time point t equals to v minus mg times t. So that's our linear velocity. So this keeps happening. Meanwhile, let's look at our rotational velocity. A rotational velocity can be expressed in a similar equation. It would be equal to rotational velocity at time point 0 plus alpha times t, where alpha is the angular acceleration of the body. This means that alpha is equal to the torque divided by the moment of inertia, and the torque, as we know, can, as shown in this diagram also, the only force that's really giving any kind of torque around the body is the friction. And this friction would give a torque of mu n times d. I'm only looking in this case at the magnitude. The direction is kind of irrelevant in this problem. All that we know is that it's, in this case, it is promoting the angular velocity to move. Meanwhile, the moment of inertia can be expressed as mk squared, where k is the radius of gyration. You might be wondering, what is the radius of gyration? Well, the radius of gyration is a quantity such that in a body, you can replace the center of mass, you can replace the entire body with a circular mass with the radius of gyration as its mass, such that it's the exact same moment of inertia as the original body. Well, in this case, we're putting our radius of gyration as k. So we can just simplify alpha to be mgd divided by k squared, because n, as we remember, is equal to m times g, and the m's cancel out. This gives us that omega t equals to mu gd divided by k squared times t plus omega at t equals to 0, which is 0, as they gave that at the beginning of the time that it was not rotating at all. Therefore, we can tell that the linear velocity that's caused by this rotation is equal to, or omega t times d, d, as I said before, is the radius of this tennis ball, is equal to mgd divided by k squared times td. Remember that the body no longer moves when omega td, equals to ft, vt. Remember that Vt and omega t are constant then. Remember, because if you see in this diagram, omega Td is going in the same direction as the friction is promoting the velocity. So therefore, Vt equals to omega Td, which when the body stops moving. And when the body stops moving, there is no need for the friction. And the friction would neither keep on decreasing the velocity, nor would it be continuously increasing the angular velocity. So therefore, at that time point, the velocities stop decreasing or increasing. Now, why are they decreasing or increasing in the first place? Well, we just see in this equation that it's from the Vt equals to V minus mg times t. Well, mu g times t. Mu g is nothing but a constant, and it would be describing a line shown as seen here. And meanwhile, omega t equals to a line shown here, with positive slope. And then, as I said, it becomes constant when the friction is no longer causing either of them to increase or decrease, which gives us the following two graphs. And if you check the answer, this should be the correct answer. Let's look at problem 14 next. Okay, problem 14 on the 2025 F equals to MA has the same context as problem 13. So it reads as follows. There are three kinds of balls that can be launched in this setup, the setup indicating the launcher mentioned earlier, all having the same radius r. 1. A regular tennis ball, a thin spherical shell of rubber of mass m1. Note that this spherical shell or solid is very important, and I will explain why later. 2. A solid wooden ball of mass m2. 3. A solid rubber ball of mass m3, where m1 is less than m2 is less than m3. All three types of ball emerge from the launcher with the same velocity. For which ball will the final velocity be the highest? Okay, let's look into this problem, and I'll see you when I look into this problem in a couple seconds. Okay, so this is problem 14. So remember that the final velocity is achieved when Vt equals to omega t times d. We can apply that here. So if we plug the two expressions that we got in the previous problem here, we get that after some simplifying of the equations, we get that t equals to v over mu g times d squared over k squared plus 1, where d is the common radius, so we can use d as a common standpoint, and k squared plus 1. Notice that this expression has nothing to do with the mass, so maybe this thing they gave us with the mass at the beginning might actually be irrelevant. If we plug this value t into the original expression for Vt, we end up getting that Vt equals to Vd squared over d squared plus k, again after a little bit of simplifying. But what is k? K is the radius of gyration. Now, I will include a proof for this in a different video. For this video, you just need to know that the radius of gyration for a solid sphere is square root of 2 over 5. Meanwhile, it's square root of 2 over 3 for a hollow sphere. And in this case, we want to maximize the final velocity, as explained in the problem when we read it, right? So how are we going to maximize the final velocity? Remember that v and d are both constants, right, for all three spheres. So what we want to do is that we want to minimize k to maximize vt, which means that we want k essentially just to be the smaller value, which in this case is square root 2 over 5, which means both solid spheres, even though their masses are different, should be the two answers and should be the two balls which will have the higher final velocity, and they should actually be the same, as it has nothing to do with the mass. Therefore, the answers should be balls 1 and 2, thus giving us our solution to the F equals to MA 2025, problem 14. Thank you.